technical problem.
I think you've got to hold it up there.
I have, if I can you see that?
No, we can't read it at the back.
Can't read it at the back. That gives me a severe problem because I've got slides coming on as well.
That ball is the introduction, the second ball is the read-only story.
Well, I don't know, I'll do something different. Then I shall turn it off. I'd like to call my talk How We Built the Control Stores for System 360, or maybe How the West Was Won. I'm going to talk to you briefly, then give you an introduction to the concepts, talk to you about the background of read-only storage up to 1961, the experience we had in Paisley, conclusions we drew, and how we set about choosing the solutions we would adopt for System 360. Then I'll go through the development story and finally show you what we ended up with, the solutions we achieved. Several speakers have explained the Professor Wilkes' concept of microprogramming. The way I like to think of it is it allowed the small machines to have a very rich instruction set by adding simply a few more words to the control store to obtain business as well as scientific instructions. Another way of looking at it is that the small machines really are emulating the paper machine that the architects have designed. Now you can make a read-only store out of either linear components, resistors, inductors, capacitors, or non-linear components such as transistors, such as diodes and cores. Transistors, of course, really would be totally inconceivable as being too expensive at that time. If you use linear components in a two-dimensional array, you have a sneak path problem. That is to say that the signals from a driven line pass through the sense lines to the other address lines and to the undriven sense lines. Therefore, you must provide substantial attenuation at each bit position. You don't have the problem with non-linear devices, of course. Now, what sort of array technology are we looking for? We want, particularly since these devices are very fast, we've got to run at machine speeds, not at main memory speeds. We want to be able to use low input power. We want to get a reasonably large output signal. We want a good signal-to-noise ratio. Of course, it should be fast, low cost, and we've got to be able to control the bit pattern, i.e. what manufacturers put into it at manufacturing time. We want to be able to control the bit pattern and know we've got the right one every time. Now, there's one key thing that I have intentionally not put on here, and that's changeability. And the reason I've not put it on is at the time we didn't know what was required. And I will come back to this point a little later on. We knew that the experience in Paisley of the ability of machine designers to get the bit pattern right was excellent. We also knew the Americans did not understand microprogramming. We knew that control automation should allow simulation of the microprograms. We didn't know how it was going to go down across the water. Read-only storage up till 1961. The ancestor, surprisingly, goes back to 1905 telephone exchange translators, which translated the pulses dialed by the subscriber into the address of the line he wants to be connected to. More up to date, the ENIAC used resistor matrices to store the function of multiply tables. This is 1947. The Russians
Oh, that's right.
Right. This was a capacitive store published by the Russians, Mr. Gutenberg of the Soviet Union, in which a two-sided board contains capacitive tabs with drive lines or address lines on one side and sense lines passing through a stack of these, a stack of planes like this. In the case where you wanted to store a zero, some sort of punching device broke this connection. Looked at this, the difficulty was that his cycle time was rather slow. The overriding problem to us was that changeability was simply non-existent. We'd have to disassemble the entire stack, remove something, put it all together again, and somehow or other assemble those connections. Now, in Cambridge, Maurice Wilkes had a core matrix in which there was one core provided for each word to be stored and one wire for each bit in the output word. No, he threaded, that was a different technology. He threaded the sense wire through the core if that corresponding bit position was to store a 1, and you omitted it, it bypassed the core for 0. Now, if you think about it, if typical engineering change will affect 3-4 words of control program, it probably means you would have to change every wire installed, every one of these wires installed. So a serious problem about that. Now there was, I'm sorry I'm having to non-spec these devices, a very interesting gadget called the thumb magnet twister, produced in the States. And it's this. Sense lines with thermaloid metal thermaloid ribbon wound around them, provided with word solenoids which drive one front for each word, one for each bit in the memory. When you pulse the solenoid, the direction of magnetization thermaloid switches parallel with the sense wire, and the flux around the wire changes, and you get an output signal. The output signal can be inhibited by placing small permanent magnets on any bit position you choose. Elegance of the device, of course, is that the storage of information is independent of the array and can be changed readily. Unfortunately, as you can see from this chart, the cycle time was about 5 microseconds, and it requires a walloping rate 1 amp to drive it, requiring the sort of power transistors that core memories use. Professor Kilburn at Manchester, I went to see the Atlas machine that Kilburn designed. It had a very, very elegant device. This is a mat of insulated wires with pairs of sense lines and pairs of word lines. And the mat was, as I remember, about so big, so high, and little ferrite rods about ½ an inch long, as I remember, would be inserted in positions where you required a 1 and omitted where you wanted a 0. The white positions here are keeper rods, which were always inserted to complete the flux path for the 1s. Now you have, I think, here an example of a balanced system with quality transmission lines and a high performance. The only negative aspect of we've got a fast machine, 200 nanoseconds, reasonable signal current, signal voltage out, and good input characteristics. The ability to automate it probably is a weakness, and I'll go on to show an improved version of that device, which was a very serious contender. Now finally, I'd like to talk about our capacitor store, which was developed in research. And I'll be talking more about this device which came back to haunt us later. Sense lines on one board, word lines on another. A card with metallized internal plane. You punched holes using a perfectly card punch where you wanted a 1, you left the plane intact, there was 0. A problem that the capacitive coupling from word to sense lines was very small, and the output signal, as I recall, was yes, for 100 volts in, you got 1 millivolt out. How you sensed the millivolts in the presence of 100 volt drive pulses, well, we'll come back to that one too. Now, what have we been doing at Hurst? I didn't know that my colleague Matt Taub was going to be here today. Matt was working on the noughts and crosses, as we nicknamed it. I don't know if you nicknamed it noughts and crosses, but we all did. For reasons that will become evident. There we are. Like Kilburn's array, we have a balanced system with pairs of address lines and pairs of sense lines, printed circuits, not a woven matrix. And in place of the ferrite rods, 2 patterns etched on a copper sheet, on a board with a copper sheet on it. And there was the X pattern and the 0 pattern, hence the noughts and crosses. Now, think of the operation of this device as the address line inducing eddy currents into these copper loops, and depending on the placement of the copper loops, you get either a positive signal or a negative signal. Now, you can see immediately the advantage of the system, that the ability to sense, to differentiate a plus from a minus signal in the presence of noise, it is just an order of magnitude advantage. Matt was achieving 200 nanosecond cycle on the bench model for 100. The signal characteristics are essentially the same as Kilburn's. Similar voltage, similar signals in and voltage out. My boss in Hursley at the time was proposing a resistor store. I don't think he's in the audience. I can point out that the weight of 125,000 resistors was a little excessive, so we will proceed. Now, the chief engineer at Hursley at the time, Charles Owen, proposed to me, I remember very clearly that he came to my office and said, Tony, why don't we take some transformers and we just take some wires and he put them through the transformers if you want 1 and leave them outside if you want a 0. Well, go and make it. So I was fairly quickly came to, this is a diagram. It's unfortunately a rather poor diagram because it gives you the impression these things are switching cord. They're not. These are linear transformers, linear ferrite. In fact, in the models you'll see that they're made of U cores and I cores, which make it together, so that you can thread these wires through them. Here are 3 drive wires shown, and this one passes through that core and through that one, and emits that one, and so on. The principle is simple. Now that was the device we came up with the scale. You can see it right here. So this was our first effort at a transformer read-only memory. The transformers are on the circumference, 64 of them. There are 30-turn windings here to carry the sense signal out from this circumference. The drive wires, which I suppose you can't see at the back, are all these things here. They start at a point such as that, go through a transformer, come outside, and we provide a rim around this wheel for wires that are not going through transformers. They sit in that rim. In addition to the transformers and the drive wires, the drive decode matrix is included on the wheel, so that for 1,000 words stored, there are only 32 by 32 connections on the drive side. The characteristics of this device are 1.5 latches per cycle, as you can see. The outstanding advantage of it is that 1 milliamp signal was produced, which is large enough to set a sense latch directly. The input power was 35 milliamps, which was what could be obtained from a logic circuit. So that we can say, put in a nutshell, this is a memory with no drivers and no sense amplifiers. There really was no other technology to touch this that I'm aware of. Now, the limitation is the cycle time. The coupling between the drive wires, there is capacitive coupling between the drive wires, there is mutual inductance between the drive wires due to the leakage inductance of the transformers. The result of that is that you get a transient zero signal through at the bit positions to which you want zero. And with this device, it took about 200 nanoseconds for the transient zero signal to die away, during which time you held off the sense latches. After 200 nanoseconds, you released the sense latches and could then determine whether you had a 1 or 0. There is a picture of scan. There is the reload memory. There was another one in the channel, in the channel. And we've got a winding tool for this device. Remember, I'm talking pre-360 still. This work terminated in the end of 61. And here is a winding tool driven by a punch card machine. There are a number of lamps around the circumference here. There's the wheel. It's bolted on, and cards are fed in. The operator is instructed to pass the wires through the transformer where the lamp is lit, and to bypass the transformer where the lamp is not lit. Changes are made by simply cutting a wire and putting in another one. So at this point we've come to, we've developed some control stores within the lab. We were aware to a certain extent of the state of the art, to the extent I've shown you, and now the 360 was to be built.
And by the way, we were assigned responsibility.
Next chart. What were the conclusions? Firstly, that you had to design with either linear inductors or capacitors. Nothing else was affordable. You needed to use printed circuits for automation, but what's the problem of changeability? There was no contender to a transformer in only store for cost, but it really couldn't be pushed below about 500 nanoseconds. That we needed a faster 2D array for high-speed systems, and that balanced 2D arrays, particularly those with complementary signals, were far superior to any unbalanced device. And I say that not only were they faster, but they were actually smaller. And many people say, how on earth can you say that when you have 4 intersections per bit in place of 1 intersection per bit for an unbalanced system? And the answer is that the coupling that you can use is so much smaller because of the excellence of the signal-to-noise ratio. The coupling that you use is so much smaller that the bit position is actually smaller, significantly smaller. Now, choosing the strategy of the System 360, because we had already built real stores, made them work, we were assigned corporate responsibility to design them for the line. We adopted a 2-technology strategy. We would use TROS for the smaller systems, and I and a colleague proposed to use printed circuits in place of the wire wheel which you remember. Here is a, because the printed circuits take up more space than the wires, we use, here are the tapes carrying the word wires. I believe, by the way, this is a very early example of flexible printed circuitry. We discovered we could really not get more than 128 tapes. There are the transformers. Here are two of them that's been removed. The I cores which mate with these U cores are here, placed in this carrier, which is contained on this frame. The U cores are pressed in place by another carrier there, a pressure plate there. Now, we can only get 128 tapes. Each tape can carry two drive wires, one on either side, there and there. So 256 words per module. We modularized the array, provided up to 16 of these modules to make a complete array. The drive tapes terminate on those two boards at the top of the module, and the SLT diode decode matrix is on the underside of the boards. There's a picture of the module. I have one here. Please come look at it. There is a tape, for some unknown reason, taken from the underside. You can see how the pattern was personalized by punching the conductors so that the current either went through the transformer or bypassed it. And the tapes were pluggable so that changes could be made by disassembling the module. So unplugging the tape, punching up a new one, hand tool, and putting it back with assembly. Reasonable flexibility to make engineering changes. There's a quite an elegant picture which seems to have got onto the cover of some magazine at this time, unacknowledged. And there's an engineering model in the lab. You can see that the circuitry, in fact these boards aren't even full. The circuitries here, there are 8 modules here and 8 on the back. And the picture that John showed you from the pages of Life magazine, there is the transformer early memory which has been pulled out to one side. There it is in place, same memory, not two different memories. And there is the model 40 complete. Now for faster machines, we knew we needed the 2D array technology, and we had maths, noughts and crosses, which I explained to you earlier, which was the build. But it occurred to me that one might be able to increase the density of this device by using capacitors instead of inductors. And so I proposed that one should use a new technology, which I call the balanced capacitor memory. Oops, that's the wrong one. I did it back again. There we are. The concept's simple. Same balance system again. 2 drive wires, 2 sense wires. You either put a capacitor across this intersection and that, or where's an example? That one and that. Sorry. Okay? Again, you've got a balance system and complementary signals out. It turns out by key thing that an engineer needs to know, I'm sure you all do, that square inches over inches is equal to picofarads. Provided the dielectric constant is 4, and as we all know, dielectric constants always are 4. So square inches over inches separation for a parallel capacitor gives you picofarads. It's a very close approximation. It's very simple to work out, but with 30 mil sense lines and, if I remember rightly, about 50 mil large signal. The limitation on the array density was simply our ability to connect to the beast. We managed to get connections on just over 83 mil centers, 83 thousandths of inch centers. We could do a bit of fan out on the edges, and we actually made connections 10 to the inch. That was the best we knew how to do at that time. Now, my management required a design competition, and Matt and I were put into head-to-head competition, and the balance capacitor turned out to have an array density 3 times higher, but essentially the electrical performance was identical. I have an array plane here. Oh, I don't know. Sorry about that. Now, so that is a plane from the balance capacitor. So at this point we're ready to start developing, and 1Q62, the whistle blew. We started on TROS, and by late 62 we got the model running, and we were into IBM product test. We were into product test in SLT with all the elegant technology that I explained to you at least a year ahead in the next unit in IBM Corporation. The reason, newfangled thing is we run the stores, nobody quite trusted it, get it in there, see if it works. It did work. We had horrendous problems with the technology. Initially the cards were paper cards, for example, not plexiglass. So you plate it through holes from wiring to the ground, to the voltage players, etc. We popped when the humidity rose, we lost connections and so on. However, we got there in the end, and we helped the components guys in Michigan, New York, go end by bringing out these problems very early in the development cycle. In January '63, to my great disappointment, we decided that we just didn't have the resources in Mersey to develop the balanced capacitor memory. At this point, only the Model 50 in Poughkeepsie was using it. We still had the 60 and 62, which elected to use conventional control. So that was transferred with 3 leading engineers to help them bring it to product, to complete product design. By late '63, a piece of excellent news occurred. A very bright, capable engineering manager called Joe Brown took over what had been the 60 and 62, became engineering manager of Model 65, and said we're going to switch to read-only memory. The guys in Kingston improved the speed of the device to 200 nanoseconds. Not surprising they were able to do it. It was the speed at which Matt's device was working and Professor Kilbur's device was working. The question being how I'm doing it. So really things were looking extremely happy. We now have Model 65, 50, 40, and 30 using control stores. The Americans looked as if they now understood what microprogramming was all about, and then the bombshell hit us in December. And I was told that the Model 30 had decided to use the card capacitor store that I showed you, which had left IBM Research, had been picked up by an ad tech group in Endicott, and I believe, the fact of the matter is that they were having trouble with their control automation system, and they just needed, or felt they needed, the ability to pull out the cards, punch up another one, put it in and see if that would work. So they decided they were going to pick up the card capacitor store. There was a big meeting in Poughkeepsie in December, which I was present, the lab director from Mercy was present, in which we pointed out in spades the problems of developing the thing. We said, yes, it could be made to work, but it would cost an arm and a leg. We weren't believed, even though we had, as I put, 12 pages of analysis to show exactly what had to be done to engineer it. And unfortunately, my management kicked me under the table in this meeting every time I spoke up. I was told, shut up, Tony, I'll fix it after. This was Fritz. So, quite simply, the truss was dumped. I was left with 3 engineers, told to build 40 or 50 models, because the Model 40 couldn't afford to wait. The first 40 or 50 were shipped to Truss, and my engineers were taken off and put on the Seacross. However, by September, key point here, 2841 file control unit being developed in San Jose, went with the Endicott team onto Seacross. Now, the volumes of the file control unit were 3 times higher than the Model 30. I mean, that's where the volume business was. And so long as the file control unit was going with that memory, they have enormous, I mean, 100,000, just perfect. Now, by September, all that we said about the file capacity came true. Costs were out of control. The thing was horrendously noise sensitive, and 2841 and the Model 40 switched back to Truss, and all was forgiven. The program was re-established and we were off and running. Fortunately, the thing was working well enough that the 9 months when there was essentially no engineering activity, we survived. John said dumb management. I think it was quite simply people could not understand that Truss was in its 3rd generation. It was being compared with a piece of advanced technology, a benchmark, and people could not understand. They were just comparing in a way that could not see what it takes to get from bench model to fully developed piece of technology. Now, if any confirmation was needed, when the Model 20 announced, that's the little one, in November, it of course used Truss as well. So the final state of play at the end of the day is as follows. I apologize for the fact that I have no figures on the Model 20. I simply don't remember them. All I know is we didn't have to do anything for it. Whatever it used, I mean, how many bits and words it used, the product, the device could provide. So we have the Truss in the Model 40, the Model 20, and the big volume item file control unit. Endicott pursued and shipped using this kind of capacitor thing. And of course we had the balanced capacitor in the Models 50 and 65. Interesting thing, isn't it? At least I thought it was. Number of bits. Whether you've got a machine that's 1 byte wide, 4 bytes wide, 8 byte wide, something to do with the instruction set gives you it must be a law of information theory. Thank you very much.
Thank you very much. Interesting talk on micro aspects. And now I know more about thank you. I'd like to call on John Fairclough now to summarise and I think perhaps manage some questions at the end, which I'm sure you'll be joining our others to answer.
Thank you very much. Well, you've been very patient, allowing us to display our egos during the day, and you've all been very quiet. I do think many of you will have questions. I hope we've left you with the impression that it was a truly worldwide effort. I think that the management of the complexity involved equates to any similar complex products that have been previously developed. I put in the same category the Airbus, presently the European fighter aircraft, many large projects where the development is distributed to a number of groups, has, seems to me, a degree of complexity that develops an esprit de corps and a cooperation, all those that are successful, that is, develops an esprit de corps and a cooperation that is an essential part of being successful. I hope I've left you with that impression that across this rather bureaucratic company called IBM, 360 was successfully developed. I won't just say despite the management, but there is no doubt the kindred spirit and the intellectual marriage that occurred between the principles involved was the dominant factor in making it all happen. As I said in my introductory remarks, undoubtedly the key individual that knocked heads was demanding beyond reason, and more often than not demanding beyond reason with Bob Evans. I think we all remember with fondness the unreasonableness that he bore down on us, particularly the point I made earlier about the building of the machine. There shall be no yellow wires on the back of the logic. All of the wiring will be embedded, and we had no way of building the machine. Now there was an unreasonableness, but we ended up with a lot less yellow wire and more embedded than we would have if we hadn't have started with that. So first summary is that it was an excellent example of teamwork and cooperation across a number of continents. Second, it may be Arabic, I don't know, but I think it did change the character and nature of computing as a result of this family of compatible machines and much of the architectures embodied. Many of those ideas and concepts you can still see today in Intel and Motorola microprocessors. So we look with pride at the part we all played in it. Let me stop talking and invite your questions.
Have you got a feel of the total number of 360s that were sold, question one, and an average price for, say, a Model 40, please?
An average Model 40 was $10,000 a month, multiplied by 50 months.
Stand up, Peter.
That'd be a smallish Model 40 as well. They were in the order of $10,000 to $20,000 anyway a month. And 50 months was the usual sort of rental period.
Total number of 360s and 370s, or just 360s?
Whatever you have in your head.
The last number I heard was 200 and something thousand individual machines built and shipped.
Could I ask you whether the spread committee made any attempt, or was it mandated, or perhaps not mandated deliberately, to survey what the other manufacturers were doing and what was going on in perhaps universities? Or
when we came together, all of us had some knowledge about what was going on in the industry, but there was no conscious effort to go and collect data about that. Whatever we knew when we joined the team was that was the state of knowledge that brought to bear on the issue.
Wasn't the attitude that you didn't really want to know about the opposition? Looking at it like, what are you doing?
Well, I wouldn't say. I mean, that's a little cynical way of putting it. There's no doubt that there was a strong feeling that after we'd spent a week or so talking to each other, there was a strong common feeling emerged that we all felt we knew what was right, and that's what got put down on paper. There was a lot of analysis, business analysis done in terms of the possible sales of this family of machines and the impact that would have not only on our competition but on IBM's installed base. I would say there was more concern about, this is an arrogant point, there was more concern about the impact that the launch would have on existing IBM installations than there was on what the competition might do.
I got the feeling that we were the youngest team in the business, and in some ways we come in with more experience from what was going on elsewhere in the world.
There was great reluctance to allow an overseas, i.e. UK group, to have responsibility for one of these machines. We won that responsibility primarily because of the reputation we developed for ourselves on SCAP. And there was some horse trading at senior management level that took place that led to Evans, although he became a great ally of ours, he was absolutely, utterly opposed to one of those machines being developed in Erskine, on the grounds that we'd never built anything, particularly we'd never built anything for volume production, and that he really wanted the 3 machines in Poughkeepsie and 1 machine in Endicott, all under local direct control. And it was only a senior management deal that was made that persuaded him. And once in fact, instructed him that the Model 40 should be developed in Erskine. And from that day forth, he turned into a supporter. He did not try and torpedo it.
Where was it built in production?
The first machine was shipped, announced April 7th, 64. The first machine was shipped about 10 months later, if I remember correctly.
I think it was exhibited at the 41 Computer Conference in 1964. With all the checking circuits. Wow.
Yeah, but that wasn't the volume manufacturing machine.
No, but it wasn't.
Were they built in the UK?
No, it was manufactured first in Poughkeepsie, in the factory of Poughkeepsie. We released it to there and to a French factory near Paris, to a Japanese factory near Tokyo, and a South American factory in Brazil. The read-only memories were made at other places. Scotland made the read-only memory for European production. Burlington, Vermont made the read-only memory for US production.
We've heard a little bit about TSO and later developments from that, but can you say something about what was the motivation for the Model 67? Was it designed originally as a prototype for the later introduction of DAF boxes and things like that, or was it purely an expedient for the time?
I think it was an expedient for the time. MIT had really spawned the idea of time sharing, and that didn't appear in our early plans, and it was a gut knee-jerk reaction to the Blau box and the what is it called? What was it called? Not the time sharing option, the one preceding TSS. That was the gut reaction, and then TSO came along later and Peter described.
It never then been it never sort of been done as a prototype for using CP67 as a
I don't know, I was gone by then. You better ask Peter that.
I think TSS and Model 67 were just a high-level thought response. We had to have something to fight general action with. It was done totally separately, a lot of it subcontracted.
But it was interesting that they fastened on to doing it based on Model 65, which is a microprogram machine, rather than the Model 75, which was the more powerful machine, because it was easier to modify and so on. So I think it was, at the
venerable designers and developers, tremendous enthusiasm you have, is that you're addressing a large-scale audience, a large-scale computer. And it seems to me the Model 30 of dots and the Model 40, the whole thing below that was not as successful as it could have been, because maybe this technology didn't scale down or scale up fast enough for you to manage to implement what you needed to do. Would you say that was fair?
I wouldn't dissent from that perspective. I wouldn't be quite as harsh in my judgment as you, but there's no doubt that you see the spread report say we have 3 operating systems.
How did it?
The spread report said that this family could be supported with 3 operating systems. Well, we did. There were Roman 1, 2, and 3. Actually, the way the report was numbered, they became known as the Happy Romans, and that got abandoned for this grand plan of a single operating system. DOS emerged because the single OSP60 wouldn't cover the line. So I think your remarks are appropriate relative to what emerged. They're not appropriate to the sort of ground rules that we tried to set in place. It really had to do with resources and cost and the attractiveness of having one operating system that would embrace the whole system. But you still ambitious.
Just tell us a few things about what then led to FS and why you drew back from that. The courageous decision to bring 360 out, apparently when it didn't need to, and then not to do FS when, in retrospect, it probably did need to.
I only admit this to my friends. I led one of the FS task forces. I wasn't involved with any of the implementation. But FS got started towards the end of the 370 as a let's do it again. And the same guy was in charge, and was Evans. It was set up initially as a competition with 2 groups. I led one, and another man called Carl Conti, who ended up running the high-end division, led the other. And we tried to recreate, again, using the power of IBM technology, a family of processors that would bring new technology and new programming and new concepts to the marketplace, making up for all of the weaknesses by then were being exposed in 360, 370. I would say after 2 years' effort and a lot of money, the judgment on FS was that the marketplace could not accommodate another revolution, i.e. that the change of programming characteristics that FS called for in order to bring in some of the more modern concepts was beyond the capacity and capability of the bulk of the marketplace. The emulation technique was still around but didn't give satisfactory price performance because there was a greater mismatch between the then 370 architecture and the architecture that was proposed for FS. And so bridging that gap with emulation was more difficult.
I think both the performance of any attempted emulation and the performance in its own native mode were both, I think, eventually judged not to be good enough.
I think of emulation of 1401 by the System 360. I felt that was a key thing. It was touched on earlier, and I would back that up, having been in the field with customers, that they could get going with that 1401 work right away, whereas it seemed an age before we could really get going with OS 360 work on a Model 30 or Model 40. Thank goodness there was good emulator there.
Ask a question. We have the countdown. I'm just a 360 man. I'm just a life a little no more. And then I went on to work with the System 38, which seemed to me to, in fact, come up and embed a matter what, to a certain extent, what sort of circuit board underneath. And it also suffered in its initial implementation from the fact that the hardware wasn't bad enough to drive the operating system. Or at least that was the user's interpretation.
I don't know. I moved away. I was by now on SNA and communication terminal systems, and I moved away from processors. My spontaneous reaction to you would be that 38 happened because FS failed.
I think it's an interpretation of it that was put on by the infantry for their program.
The probably a helpful story about FS is, as you probably know, it was developed about Model 38. It was developed in Rochester. Well, Rochester is in the northern part of the United States. It gets very cold there. Yes. I can attest to that. And the story goes that it was so cold there, very few people went there, and when FS stopped, nobody told the people in Rochester. So they carry on, and the AS400 is a splendid system today, and in many respects, it met many of the FS goals for having a store which you didn't have to know where being planned. But if I go back to a previous question about the failure at the bottom end of the line, I think myself that one of the recommendations of the spread report wasn't followed through, because the bottom end system was just a card system. And we didn't implement that in 360. And therefore, the 360 series were all to be attended by people with white coats and air-conditioned rooms. And this is where the System 3, System 36 saved IBM's native, because they could put machines in to people who didn't have system support staff. And this, of course, should have been what System 360 did at the bottom end, but its operating systems, not the hardware, the operating systems wouldn't support that kind of operation.
Another big fight we had before announcement, but in the 9 months it ran from 9 months before to about 3 months before announcement. John Hanstra, who started as chairman of 360, if you remember in my introduction, he managed the medium systems and was responsible for 1401. He quietly, as an underground project, as the technology was developed to support this family of 360, he took that technology and also used that technology to build a 1401. And that was known as the 1401S. And so that was his benchmark in cost performance terms of whether the Model 30, including its emulator, would satisfy the market for which he was responsible. And of course, the 1401S looked at narrowly for a narrow set of applications, was somewhat superior than a Model 30, even with the emulator. And there was a lot of blood spilled on whether the Model 30 should go with this family. This is again underscoring your point of its emphasis, and whether the 1401S should go instead of the Model 30. As I said, in the end, 30 went ahead for family planning reasons.
Overnight, the team working on Model 30 went from 13 people to 97.
You gave us a very interesting lecture there on microprogramming, but have you seen the death of microprogramming with the RISC technologies?
Well, that's the epitome of microprogramming in many
There, interpolate with a retarding note. Today's smooth presentation has given us a very good picture of the engineering development, but reading Professor Brooks' delightful book on developing the writing the OS indicates that the sort of brute force, no expense spared method was ludicrously inefficient.
Correct.
Now, in this loving environment of IBMers here, to which I don't belong, I may add, would it be possible to mention perhaps some of the ludicrous inefficiencies in the engineering development? And secondly, may I comment that the 360 had a remarkable take-up in this country, and to me it represented a gross retarding of technical computing in this country, because it had a thing I do not understand, a paranoid aversion to algol. Now, it was absolutely ludicrous. It went on for years, and I've heard delightful, charming IBM salesmen telling me that, well, reluctantly there is an algol compiler written by IBM. It is grossly inefficient. Don't use it.
I think the answer to the algol point you make is simply one of home built. IBM, an IBM employee invented Fortran, and that spawned then a wide effort in the development of Fortran compilers. And
this didn't invent Grace Hopper.
Well, COBOL, IBM did support COBOL. I mean, very adequately. But this was in the era when there were two worlds. There was a scientific and commercial world. So I would say the bigger arrogance of IBM was saying we're going to replace all of that with PR1.
Yes, but nobody took up PR1. I did. I thought it was marvelous, but nobody else.
We developed that in Hersby too.
The interesting thing about algol is they had to take all the output statements from Fortran to make it work.
Yes, of course they did. Algol was free of it.
Here we go. On your point of inefficiencies in the engineering, there were clear inefficiencies, but by and large, the inefficiencies that existed there were competition. You heard reference in the presentation of machines trying to reach a performance level that would in fact challenge the cost performance characteristics of the machine above. That competition was very well developed. There was competition on technology, but I would say that sort of internal competition produces inefficiencies, but it also produces better machines at the end of the day. And so I would say on the hardware side, the inefficiencies were by and large productive. On the software side,
we didn't have that wide range of skill and expertise over a number of sectors that you have with the hardware.
Oh, that's not true. When I was involved with PR1, I had people in California, in Vienna, in Boston, in New York.
Working on a project.
Yes.
I'm talking about the backlog of experience that you had in hardware. You've been developing these things for a large number of years. You didn't have that class. What software did you develop before PR1?
Oh, I mean, languages, they were supreme in Fortran. No problem. Fortran was a good foundation for COBOL. In terms of operating systems, it was 1410, 1710 operating system, though it wasn't widely known. It was the best disk operating system in the world, by a long way. There were no other really disk operating system designed for disk other than the 1410, 1710 operating system. And those are the people who eventually produced OS. I mean, the only person that I recognize as a programmer on the spread committee was Phil Heising, who was a Fortran man, and Joel Aaron, who was a FSD applications man.
by the way, Fred Brooks has just published the second edition of the Mythical Man Month. He sent me a copy, and he adds a number of chapters critiquing his conclusions of 20 years ago, where he thought, even in today's terms, he was still right and where he was wrong, and adding some perspective on the future. It's a very nice, and it's very eloquently written.
It's a marvelous book.
What's the title?
It's the Mythical Man Month, the second edition. I wrote to him yesterday and said my market forecast is it sell more than the first edition because the value added of what is put in there will encourage everybody who bought the first edition to buy the second edition as well.
Can I just
They publish it, yeah.
Can I just change the subject?
A final question, that's it.
And thank you, John, for this presentation, because as somebody in whose mind the announcement struck absolute terror,
I very much appreciate everything you've had to say. I was in ICT at the time, and Arthur Humphreys, Basil Franklin, myself, one or two others, were over in RCA in April '64, deciding what the hell we should do about our product range. And we were having one of these 2-week sort of love-ins with RCA, where we were looking at this incredibly disparate range that we had between us, from the FB6000 through to the 301 and the 501, the 1301 and all these damn things. What the hell were we going to do? And RCA produced grand ideas for all sorts of marvelous processors. And then out of the blue came this invitation, because RCA were an IBM customer, an invitation to attend a product announcement. So I said, why don't you come along? So we went along and, well, how do one describe it? We were totally gobsmacked. It was, first of all, the first razzmatazz presentation of the computer system I think that there was. And of course it threw everything we'd been talking about with RCA into total confusion. So they went away, we said, well, we'll retire for a couple of weeks or a week while we each think separately. When we went back, they said, we've reviewed all our plans, and they announced a product range which was a straight copy of what had just been announced. Join us. We will fight them on their own ground, you see. Now, Arthur and I said, rubbish. If we do that, we're certainly broke. It was all right for them. RCA had lots of other revenue flows. Our only revenue flow was from renting computers. So we had to keep it going. And how could we change over? We hadn't got the technology that you had, anything like, and our costs were going to be at least twice yours. In order to sell anything, we'd have to undercut you. So it was quite a hopeless situation for us, and that was where the parting of the ways between ICT and RCA came. So we went off and we produced a product range of our own, based on the 1900, which at least kept us afloat for a very long time.
Of course, the irony is ICL and Fujitsu got together on IBM compatible machines.
Very much later on. Here again, that is an irony, maybe, but it's also the case, is it not, that Fujitsu could only get where they were because they weren't dependent on a revenue stream from data processing customers as we were. They could afford to have lots and lots of money going out. We could never afford to have any money going out. We couldn't afford to make losses year after year, as Fujitsu could, as Siemens could, as English Electric thought they could. So it's a very different situation. And in the end, I think we made the right decision, but it was very tempting. But it wouldn't work.
Final question from